Let me share my screen. All right, so the plan for today is to go over modeling transformation. We started with translation last week, and we have seen a 2D translation in matrix form, but we ended the lecture with an exercise saying that how can we translate the point to a new location, or how can we find the coordinates of the translated point, not with matrix addition, but with matrix multiplication. And we actually started solving the question and this exercise, and basically said that a 2 by 2 matrix is not enough. We cannot do that with a 2 by 2 matrix. In order to perform this linear transformation in 2 dimensions, we need a 3 by 3, actually even a column vector. I mean, here, if you look at the translation matrix, it's also a 2 by 1 matrix like this. It's not a 2 by 2 matrix. Here, what we will do is we will find ourselves methods to write the new coordinates. So if you want to write x prime, the new coordinates of a vertex with respect to the previous coordinates, it has xy coordinates and with some constant number. Okay, let's call this constant number c. So this will be a linear transformation, ax plus by plus c. So okay, so we can add to the original coordinate a constant number. For example, if we want just translation, what do we want here? If a is equal to 1, if b is equal to 0, if the c is equal to tx, what do we have here? X prime becomes x plus tx, right? So translation simply is a linear transformation. It's linear because, as you can see, we write the new x coordinate as a linear combination of its coordinates, of its existing coordinates, ax plus by, plus some constant. So this is a linear equation, and this is called a linear transformation. So the constants here determine what kind of linear transformation it's going to be. The interesting thing is that all translation, okay, translation, rotation, and scaling, the basic transformations that we are going to perform, they all three of them can be written as linear transformation. They're all linear transformations. That will be these coefficients. Here for translation, the coefficients are 1, 0, tx for x prime. But it will be different for rotation, and it will be different for scaling. But at the end, we will be able to write the new coordinate with respect to the previous coordinates as a linear combination of the previous coordinates. So this is therefore the transformations that we are going to see here are linear transformations. And as you can see, the x prime is found by multiplying the previous coordinates with some constants. 3 of them are multiplied with 3 other things. So it's going to be something like this. If the translation matrix we have, if t is, if you look at the first line, if I put there 1, 0, tx, the coefficients that I used here, and if I multiply this with a column vector which is x, y, 1, its previous coordinates, and this 1 is for that constant part. In other words, whatever I have here is going to be multiplied with 1, and it's going to be added to the new coordinates. So how do we perform matrix multiplication? We get the first row, we multiply it with the first column 1 by 1, and we find ourselves the new x prime coordinates. So 1 times x, 0 times y, 1 times tx, it gives me just x plus tx, and that's x prime. So what should be the second line? What's going to be y prime? If I want to translate a vertex, the y coordinate, it's going to be y prime is going to be y plus ty, because I want to move it ty amount in certain direction. If I want to do it like this, what should be the coefficients? 0, 1, and ty, right? And since this last one, it should also be like, this is what we have here, the coordinates, two-dimensional coordinates, represented as three-dimensional points in which the last entry is always 1. This is called homogeneous coordinates. And we just use this last coordinate not to indicate a position here. As you can see, it's we just use it so that we can have the translation as matrix multiplication. So the last one here should be 0, 0, 1. Therefore, we are going to get 1 in the new one as well. Okay, so this matrix here, 1, 0, tx, 0, 1, ty, 0, 0, 1, becomes my translation matrix. And this is my vertex coordinates. So if I multiply, if you have an object, if you have a triangular mesh, okay, it may be a very complicated object and you want to visualize it in ray tracing, for example. And what you want to do is, let's move this to some place. I want to visualize the same thing and I want to move it to some other place, and I want to change its coordinates. So what you need to do is, whatever number of triangles it contains, you have to move all of these vertices of those triangles and then render this. And the way to do that is, if you have this object and all of the vertices, if you multiply each of the vertices with the same, as you can see, this is constant for that fixed modeling. So for modeling transformation, we are going to apply, if you want to translate the entire object to a new place, the same translation matrix is going to be applied on all of the vertices. So you have to multiply all of the vertices with this t. Okay, so this is how we can apply. If you apply that, if you find the new coordinates of all of the vertices, then you render the object. It will have an effect of that object is moved to a different place. If you have another object and if you want to move it to someplace else, you multiply it with another matrix, let's call it tx2, ty2. So based on the translation parameters you have, you may apply different matrices to move the objects. Right now, this multiplication of matrices with objects may seem to you as overkill. Okay, I mean, if you're just going to move an object, I already have the vertices, right? Why do not just add these numbers to them directly? It will also have the same effect. And if your goal is really just translation, you may as well do that. Okay, so what we are doing here, multiplying everything with matrices, if you're just doing translation on all these vertices, it doesn't seem the right way to do. I mean, it seems like an overkill. It seems like too much to do. Instead of just adding these things, why do I need to do multiplication lots of times? But we are going to see that. The next algorithm we will see in our computer graphics class, the forward rendering pipeline. The algorithm actually is all based on the forward rendering pipeline. Is based on matrix multiplication. And what we will be doing is this. We will be asking this question. Given a vertex of an object in my three-dimensional scene, now it's called, the ray tracing is backward rendering pipeline, because we start from the eye and we we shoot a ray through the center of a pixel. We start with the rays. Now, this is like an object-oriented version of rendering, because we now start from the objects. And if we have an object in the scene, like this object, imagine we have a vertex here. Imagine we have a three-dimensional triangle. Now we will ask this question. It has three vertices, v1, v2, v3. We will ask this v1 on the image plane, on the image plane, where does v1 going to, where is V1 going to appear on the image plane? Where is V2 going to appear on the image plane? Where is V3 going to appear on the image plane? If I can tell you V1 is going to appear here on the image plane, V2 is going to appear here on the image plane, and V3 is going to appear here on the image plane, you can see that there should be a triangle that appears like this, and this 3D triangle is going to appear like this on the image plane if you know where those vertices fall on the image plane. Now, what I'm going to tell you is that this step, finding an arbitrary three-dimensional vertex in the scene, and in a perspective view, we will have also a perspective view, answering this question, which pixel does an arbitrary vertex, if I just give you the XYZ coordinates of this vertex, can you find which pixel on the image plane it's going to fall onto? This question will be answered with just this. We will find the matrix, we will multiply it with V1, and it will give us the coordinates on the image plane. Okay, the image X, image Y coordinate is going to be given to us by multiplying the whole algorithm. The entire, this is not the whole algorithm, because after we find V1, V3, V2, these vertices, obviously we have to fill in the pixels in between if you want to fill this triangle, right? But this is a very crucial, like half of the algorithm is figuring out where an arbitrary object's vertex in the scene, in the three-dimensional world coordinates system, where it falls on a 2D image based on, again, camera parameters, where that image plane is, where is the eye located, what kind of a perspective vision we have. But what I'm telling is that in the next couple of weeks, we will see how to compute this M matrix, okay? And it will contain, this M matrix is going to contain modeling transformations, camera transformations, and projection transformation. It will contain 3 separate parts. Modeling transformations is going to be like matrices that are like this, is going to tell us, okay, this vertex 1, it was in the file when we read this object, V1 was this, but that V1 is actually moved to this location. The object is rotated this much. If you have, these are modeling transformation, and that will be the first ones that are applied on V1. And then you're going to ask this question. Okay, we have a camera located at an arbitrary location. It's looking in this direction. But what if I want to change the entire addressing of the world space in such a way that camera is at 0, 0, 0. It's looking at minus z-axis. Okay, so I want to change. It's like we will have a coordinate transformation saying that, okay, let's make camera at the center of the world. But the thing is that the camera, you don't want to move the camera. You still want to view the entire scene from a particular angle, from a particular position. So if you want to move the camera to origin, you have to move the entire world along with it so that you get the same view. So, but what we are doing in that sense, we are going to see it maybe on Thursday, this part, is going to be an entire addressing change. We will change our world coordinate system, saying that, okay, let's make, the camera was, for example, at 575, but let's make that 575 now 0, 0, 0. The addresses are changed. Now let's make this axis, this arbitrary axis that is coming out of the camera eye, let's make it the minus z-axis. Let's make the up vector the plus y-axis. So we are going to change the entire reference frame, and guess what? That world transformation, coordinate transformation, will be nothing but a single matrix multiplication. So it's going to be like we are having V1, we have modeling transformations, let's call it, let me call it the matrix of modeling transformations. Then we are going to change the entire addressing, the matrix of coordinate transformations, and at the end we are going to have, okay, we are going to have perspective projection. Our goal will be in perspective projection, will be in this new coordinate system. Where does V1 projected on the image plane, and that will also be another matrix. Let's call it projection transformation. Okay, look at this. Modeling transformation, coordinate. Try to concentrate on this part. The entire board is too crowded, sorry about that, but concentrate on this part now. I have a vertex, I change its position, I rotate it by modeling transformations, then I change the whole entire addressing of the world with coordinate transformations or camera transformation, and then I find the location of the vertex on the image plane with a projection transformation. And all of these are matrices, and they will all be 4x4 matrices in the three-dimensional world. Okay, if you're trying to render a three-dimensional world, all of these will be 4x4 matrices. Now, the good thing is that matrix multiplication is associative, meaning that instead of doing it like this, first doing this, then doing that, then doing this, okay, instead of doing that, what I can do is I can multiply all them together, and I can get myself a single matrix like this M. And with that M, I will, when I multiply it with, if I multiply it with all of the vertices of an object, I will find all of the coordinates that those objects vertices fall on the image plane. So this is forward rendering pipeline in a nutshell, this first part. That's why matrices, making the modeling transformations in matrix form is so important, because we're actually unifying an entire algorithm. Its different parts is unified as 4x4 matrix multiplications. So this is something really, I think it's a really nice algorithm. And actually, one thing you can ask at this point is that, is perspective projection transformation, how come it's linear? It doesn't seem to be a linear transformation. And actually, you'll see that it's not a linear transformation. This fourth dimension in 3D world, we will have something like this. I call it the fourth dimension. It will be like XYZ1. Okay. In 3 dimensions, we will have this 4-dimensional column vectors. We are going to call, instead of having 1 at the 4th dimension, we are going to have a W. And this will be used to model that non-linearity in perspective projection transformation. We are going to come to that later. So I'm actually summarizing what we will be seeing in the next 2-3 weeks. So, okay, so if it's okay if you cannot follow this entirety, but just before we proceed on why do we need to multiply everything with matrices, just I wanted to give you a heads up on why matrices are important, because the entire algorithm will be multiplying 3 big matrices, and the whole algorithm, the first step of the algorithm is this multiplying a given vertex with a matrix. And actually this is in programmable shaders. This part is done in what is called vertex shaders. So if you called vertex shader, if you have ever heard this term before, that's the whole, the goal of a vertex shader is to given a vertex, figuring out its coordinates on the image plane. Okay, so we are going to come to those later, but as I said, this is a heads up summary of what's coming up ahead in the upcoming weeks, and that's why we don't want to translate a given point with just p plus t. We want to write a matrix that is like this. So the solution will be, if I sorry, not this one, it's this. If you want to translate a point, let me write it from scratch in a new thing. So given a point p, x, y, z in 3 dimensions, and if you want to translate it, you want to have a function. Let's translate this point, and these are my parameters. So any translation or any transformation, rotation, or scaling should come with some input parameters. So this tx, ty, tz is the dislocation amount. I want to move this point P, tx, ty, tz amount. This can be, for example, -3, 4.1, minus 0.1. They may be floating point numbers like this. And after I move this point, any point, if I displace this point with these parameters, what will be the new coordinates? What is P prime? In all these modeling transformations, our goal will be to find a matrix for this modeling transformation in which we can apply it generally on any point, and that point will be moved this much as a result of this matrix. So here, the translation matrix will be 1, 0, minus 3, 0, 1, 4.1, 0, 0, 1, 1. Actually, there's also, oh, actually, I forgot the third dimension. I'm writing it 3 by 3 matrix. It should be actually, I forgot this additional 0 here for the z-axis. This should also be longer like this. 0, 1, 0, 0, 0, 1, and the last row is 0, 0, 1. This is 4.1, and this is minus 0.1. So this matrix will be my translation matrix for any point. So given any point with xyz coordinates, I will multiply it. I will right multiply. That's also very important. So I have a 4 by 4 matrix. I right multiply it with my point. This is a 4 by 1 vector. And the result will be another 4 by 1 vector. This x prime, y prime, z prime will be the coordinates of P prime. And as you can see, each row here, a row of this modeling transformation matrix, is a recipe. These are instructions that tell me how that linear transformation of the previous coordinates are applied. These are all, if you think about the columns, these are like x, y, z1. It tells you these are the coefficients of that x, y, z1. It tells you that the first, each of them are recipes for individual coordinates, that is for the new point. So x prime should be 1 times the previous x coordinate plus 0 times the previous y coordinate plus 0 times the previous z coordinate minus 3. Okay, so this is how you're going to find the new x prime coordinate by multiplying it with this. All right, is this clear? Are you having any difficulty following me? If you have any questions, you can ask at this point. Now I'm going to, if you don't have any questions, I'm going to now talk about rotation. How can we have rotation, rotate a particular amount? I will first start with 2D example, and we will then jump to, we will actually talk about 3D. Yeah, probably if we have time, I will talk about 3D rotation, but in 3D rotation, we need to have another parameter, which is the rotation axis, and 3D rotation actually takes a number of steps. So that's the most difficult of those modeling transformations, rotation around an arbitrary axis. Okay, all the other transformations are so simple, but let's start with the 2D case. And also, you may have, at this time, you may have wondered, okay, the new x prime coordinate, can it ever, are all of these two coefficients there, are they always going to be 0? For example, can the new x prime coordinate of some point, maybe something like this, 0.4x plus 0.6 y, can it happen something like this? Why does the new x prime coordinate depends on the previous y coordinate? When can this occur? It cannot. Exactly. For translation, this will never occur. For translation, it will always be 0. But for rotation, you're going to see that this will be, there may be a non-zero coefficient for the y coordinates. So let's go ahead and start with that, and let's try to solve 2D rotation case. And here is the problem that we try to solve. In 2D rotation, first I'm going to show you rotation around origin and what it means. Okay, so let's assume this is 0, 0. I have a point P with some coordinates. Let's call them x, y. Okay, now I want to rotate this point around origin alpha degrees, okay? And the rotation around p, around alpha degrees, correspond to this. So I try to do it like an arc on a circle, because this is what happens in rotations. So this alpha degrees, let's have it like this. So this is alpha degrees. And the degrees in rotation, the positive rotation angle is always counterclockwise. It's like we follow the right-hand rule. If this is the x-axis, if this is the y-axis, the positive z-axis is towards you. So the rotation is around like positive z-axis, and your fingers, your four fingers, show the positive angle of rotation. Okay, so it will be in 2D, it will be like, if you're rotating around an arbitrary axis in 3D, what you need to do is that arbitrary axis should also have a direction. It should not just be a line. The axis of rotation should be directed, and which will tell you, which you will actually use your thumb to go in that direction of the rotation axis. And then the other four fingers, their orientation, the fingers are pointing towards the positive angle of rotation. So if I, for example, want to rotate p minus alpha degrees around this origin again, it will be towards this way. Okay, minus alpha will be rotating in this direction. Now, let's try to see this. If the only thing that is given in this case is alpha, that's the only parameter. By just knowing alpha and knowing x and y, can you figure out what is x prime and y prime? And try to write x prime in terms of these three things. You only know the previous coordinate, you know alpha, and what is x prime and x prime and y prime in terms of x, y, and you're allowed to use alpha. You have to use alpha because alpha determines your new coordinate. So that's our goal. What is x prime and y prime? Here's how we're going to proceed in finding the rotation matrix. Again, we are going to, before the matrix, actually, we can try to derive equations for x prime. So we want to do something like this. If this is really a linear transformation, x prime is going to be something like ax plus by plus c. Okay, it has to be something like this. But what is a? What is b? What is c? We are going to figure this out. And here's how we are going to derive this. The thing that is invariant in this rotation is the distance of this point p or p prime to origin. Okay, so when you move, if you rotate something, if you imagine this p was connected to origin with a rod, and if when you rotate p around origin alpha degrees, the length of this rod stick does not change. Okay, so this d is the same in both cases, and we are going to make use of this invariant in deriving our formula. Let's call this angle here theta. Okay, now if I call this angle theta, I can write the coordinates x and y in terms of theta, right? Here, the x coordinate here in p is going to be d times cos theta. If I do any mistake, so I may be making mistakes, okay, while I'm doing it, please interrupt me and correct me whenever you see a mistake. And the y coordinate of the original point is equal to d sine theta. Okay, now I can write x prime and y prime similarly, but this time what will happen? What is x prime? What is its cosine here? If you look at the angle, it's alpha plus theta, right? So if you look at the x prime coordinate, it's alpha plus theta. And similarly, y prime is d times, because d was the same thing here. And at the end, you are going to see that you're going to get rid of all these d and theta, we will get rid of them in the final equation. We're not going to be needing them. So here, d is sine alpha plus theta. Now, here's the place where we need some trigonometry. Okay, I will need some help from you guys because I don't have these formulas memorized in my head. So you remember from high school, maybe, I mean, if trigonometry is still taught at high school, we were able to write, if you're given some cosine like this, it's possible to write this cosine in terms of multiplication of sine and cosine of these individual angles. But I don't remember those formulas. So cosine alpha plus theta, what was it? Is it sin alpha plus cos theta minus cos alpha? I mean, there should be four sine cos terms in both of them. Especially, we are also going to write the other thing as well. Sine alpha plus theta is also equal to something. Perfect. So the first one, cos alpha plus beta, so the cosines are multiplied and sine are subtracted from that. Thank you very much. So what we have here is cos alpha times cos theta minus sin alpha times sin theta. Now, let's write x prime. Let me first erase this part. So I have to change this. Yeah, let me first erase this part. And underneath, I'm going to write x prime with the help of this new knowledge. And after that, I mean, doing the same thing for y prime will be trivial, but you're going to see what we'll have. So if cos alpha plus theta is this, what I'm going to do is x prime is equal to d times cos alpha times cos theta minus d times sin alpha, or sin, let me just be consistent, sin alpha plus sin theta. Okay, so this is what x prime is. So we still have d and theta here, but does any of these terms seem familiar to you from what we have written up here? Yeah, it is. Look at this, d cos theta. What is d cos theta? It's the x-coordinate. It's the previous x-coordinate. So x prime is equal to the previous x-coordinate times cos alpha minus what do we have here? D sine theta. What is this sine theta? It was the previous y-coordinate. So minus the previous y-coordinate times sin alpha. Okay, so what we just did was we have written x prime as a linear combination. So this sin alpha and cos alpha, they're just constants because alpha is given to us. Okay, alpha is given to us. You just find sine alpha, cosine alpha, and they're just become constants. You just written x prime as a linear combination of the previous two coordinates. Let's do the same thing for y prime. For that, we are going to need what this sine alpha, alpha plus theta. Let me guess this one. Is it? This should be then the other one in which sine theta, cos alpha, sine alpha, cos theta plus, how was it? Yeah, perfect. Thank you, Bugra. So it's, they're all, sine alpha, cos theta plus cos alpha, sine theta. So you just add the variations of these two things. So cos alpha sine theta. Okay, if you just write the same thing here, this time for y prime, what it happens is that it's going to be d times sine alpha, not d times, x times sine alpha plus y times cos alpha. It should be something like this, right, if I'm not mistaken. So yeah, y prime is just written there. So in other words, if I have this matrix, cos alpha minus sine alpha, and then sine alpha, cos alpha, and 0, 0, 0, 0, 1. If I multiply it with any xyz point, any xy point in 2D, what do I get? I get my p prime. Okay, so we just derived a rotation matrix, rotate around origin in given alpha degrees. So as you can see, this is some general formula, a general recipe, general set of instructions that tell you if you want to rotate a point around origin alpha degrees, all you need to do is form this matrix, cos alpha minus sin alpha, cos alpha. I don't even have this matrix in memory. But you know how to drive it. This is rotation around origin. It's not too difficult to memorize. Actually, I could have memorized this. But if you multiply this with your point, it will have the effect of rotating your point around origin alpha degrees. And this rotation, when you apply it for triangles, for example, if you have a triangle, if you apply the rotation, let me have it on a new piece of paper. So if you have a triangle like this, okay, and if you rotate it around the origin, for example, 45 degrees, it will be in different orientation. Its orientation is going to change, its location is going to change. So if you apply these to its vertices, V1, V2, V3 separately, it will be at these new coordinates rotated and rotated nicely around origin 45 degrees. All right, so this is how we get rotation. Now, in the last 15 minutes, I'm going to talk about something, a problem that seems like a more difficult problem in the context of rotation. What if we want to rotate an object not around origin, but for example, if you have a triangle like this and you want to have an animation in your program in which this triangle rotates around its center of mass. So what you want is, you want an animation in which this will rotate all around itself. Just you understand what I mean. So if you want to rotate it around its center of mass, but not around origin, how can you establish this? How can you rotate a point? For example, now here's the problem that I try to solve. I have a point P. This is point P. There's another rotation point. Let's call it R. Exactly. So thank you, Bugra. That's actually, this is the thing that you will be doing a lot when we have these complex transformations. So the problem that we try to solve is this. We want to rotate this P around R alpha degrees. So this is P, this is P prime, and this is alpha. So we want to do this. This problem would be very simple if R was the origin, right? So why don't we do it first? So what we do is, the first is move R to origin along with the points. So when move everything, move the whole setting so that R is the origin. All right. So if you do that, what is the translation to do that? In order to, I know the coordinates of this to be Rx and Ry, what I need to do is first apply a translation with minus Rx minus Ry amount to the point. Okay, if you do that, the point will be moved along with R, and the amount of movement will be exactly equal to this minus Rx Ry. If you apply this minus Rx Ry to R, it becomes 0, 0, right? So it becomes the origin. Then do the rotation alpha degrees, rotate around origin alpha degrees. But when you do the rotation around origin alpha degrees, P prime becomes here because P was moved here. Now the rotated one is here. What do you need to do? You need to move, as Bugra said, you need to move the R, this point R, back to its original place. So if you move R back to its original place, it's T Rx Ry. So these translation, let me write them here like this: T minus Rx minus Ry, rotate. This is my, I only know this R matrix can only do rotation. Let's assume we have this R matrix, which gives me rotation around origin alpha degrees. So let's forget about this now. And then another translation with Rx Ry amount. So you have noticed, actually, right now I'm doing this very naturally because I'm used to doing this a lot. But one thing you may have noticed at this point is that if you read the matrices from left to right, it's actually the inverse of the order that we apply them on the point, right? I mean, because the point is here. Multiplying the point with this matrix, what does it give you? It has the effect of moving the point, moving R to origin. So this is the first thing that is applied. Then perform the rotation. So this is step one. Then perform the rotation. It gives you the result. If you look at this result here, what is the result here? It's this P prime. It's this P which is not moved back to its place. Then move it back to its place. This is the last. The third step appears at the leftmost. Okay, so this is something very interesting because we have these column vectors and we multiply our points with the right of these matrices. The effect is that when you're reading these matrices, you have to read them from right to left, or based on their proximity to the point. The closest matrix to the point, to a vertex, is the matrix that is applied first. Okay, you get a new point, then you apply this matrix, then these are all these transformations that are applied on this matrix. They appear like this. This is the first one applied, second one applied, third one applied. And the good thing about these matrix multiplications, again, is they're associative. What you can do is you can compute the entire rotate around arbitrary point matrix. If you do it will not be very difficult to do the multiplication, right? Actually, you can do it by hand. Well, if for example, if you're given two things, alpha, Rx, and Ry as your parameters. These are your parameters. The point R, let's call it the pivot rotation point, Rx, Ry. You are given two things. Given an arbitrary point P, find a single transformation matrix which will rotate this point P around R alpha degrees. So here's what you need to do. My arbitrary rotation matrix is going to be this: 1, 0, minus Rx, 0, 1, minus Ry, 0, 0, 1, and I have this cosine alpha minus sine alpha, 0, sine alpha, cosine alpha, 0, and then 0, 0, 1. And finally, I have 1, 0, Rx, 0, 1, Ry, and 0, 0, 1. Okay? Everything, and look at these three matrices. Everything in these matrices they contain values from your input. Alpha. If you know alpha, compute cosine alpha, sine alpha. Just plug in this matrix. Rx and Ry, they are also given as input. You can just multiply these three matrices together and you will get the formula. Each line will contain a formula that tells what is P prime, what is X prime, if it's x prime, y prime, the first line is going to give you the recipe to compute x prime from these entities. Okay, so this is called a composite transformation. It contains 3 steps. We solve a seemingly difficult geometric problem by applying successive operations on our point. The purpose of this one and this one is this translation is to make our life easier. Okay, we make our life easier in terms of rotation with this, and we apply the actual rotation is applied here, and whatever we did to make our lives easier, we have to undo it because we are living in this other world where things are difficult, where the arbitrary rotation pivot point is the pivot point is an arbitrary point. So we get back to that world by undoing this thing that we did earlier. Okay, so this contains 3 steps, and this is how rotation is applied. Now, in 3 dimensions, so actually in the last 5 minutes, I can quickly talk about, since we know this, we can compose how to do things in a more difficult way. Now, what we're going to do is, if somebody gives us in 3 dimensions, it will be really difficult. My drawing is really bad. I don't know how I'm going to do 3-dimensional things here. Maybe I can just refer to the PowerPoint figures. Yeah, let's have a cube. Imagine I have a cube here. Okay, and I want to rotate the cube around this axis. Okay, this is the axis of rotation. This is the axis that is given like this, and the rotation is going to be this way, right? If you put your thumb with the direction of the arrow, the rotation will be your other fingers, your right hand. You have to use your right hand like this. And it's in an arbitrary location. This is Z, X, and Y. Okay, and we are given an arbitrary axis, and we want to rotate our cube around this axis alpha degrees this time. Now, the idea is the same. We will do the same thing because what we will have a rotation matrix that can rotate this cube around z-axis. For example, the rotation around z-axis is very similar to what we have, because the rotation around z-axis is like 2D rotation around xy, right? It will be very similar. It will be like this: cos alpha minus sin alpha 0 and 0, sine cos 0 0 0 0 1 0 0 0 0 1. So the 3D rotation, as you can see, this is a 4x4 matrix, but rotate around z-axis. When you rotate an object, if you have an object and you rotate it around z-axis, the z coordinates of the objects do not change. Only the x and y coordinates change. Then the rotation around in 3D, rotate around z-axis like this, is a matrix like this. Okay. Now, here is the thing that we will need to be able to use this easy matrix that makes our lives really easier. Our lives will be really easy if the rotation axis was the z-axis, right? So that's what we're going to do. We're going to take this arbitrary axis. For example, how can we do that? We're first going to move this corner of the cube here, and then we are going to apply a rotation on the cube. Actually, it's going to be 2-step rotation, such that this part of the cube is going to be on the z-axis, and then we are going to have this axis aligned. The first 2 operations we are going to do, actually it will be like 3 steps. First is translation, get this point on the origin, and then perform a rotation. Actually, there are 2 angles that an arbitrary vector makes. One of them is with the xz plane. First, we're going to get it down, and then we're going to rotate it so that it's aligned with the z-axis. So it's, for example, if it's an arbitrary vector like this, we first put it on the xz plane, and then we move it. So there are 2 different angles actually. They will be like theta 1 and theta 2. Okay, these two angles, one of them is how far away, how high the vector is from the xz plane. The first thing we will do is make the rotation so that it's on the xz plane. After it's on the xz plane, we are going to pull it, move it this way so that the axis is aligned with the z-axis. After that, our life is very easier because our rotation axis is now the z-axis. Perform the rotation and then undo everything you have done, the 3 steps for the undoing. So in a total of 7 steps, we will be able to rotate in 3 dimensions, rotate an object, rotate or a vertex around an arbitrary axis. This is the most difficult rotation that we will do. But if you get this idea of composing transformations by in multiple steps, this becomes not so difficult. All right, so I'm going to go over the slides on Thursday. Today we mostly use this whiteboard, but on Thursday I'm going to go over the slides so that we see if we are not missing anything, and we are going to finish modeling transformations, and we will answer this interesting question on Thursday, which is this. For example, you have an object in 2D. Let me give you a coordinate system. This is my origin, this is the x-axis, this is the y-axis, and I have a point with a given xy coordinate. Okay, now a new government takes over and says that, okay, who told us that this is the origin and this is the x-axis and the y-axis? Now I make this point the new origin. This is the new origin, this is your x-axis, this is your y-axis. Okay, what is the coordinate of the same point in this new addressing scheme? Okay, so this is p new. Look at this. If the origin is here, oh, it had a positive x coordinate here, but in this new coordinate system, it doesn't have a positive x coordinate anymore. Luckily, it still have a positive y coordinate, but it may be different than the other one. So that's the question we will be answering in weaving transformation. If in this new coordinate system, if somebody gives you the parameters of this new coordinate system, this is the with something like this. We cannot say this is 0, 0. As you can see, this has actually a coordinate. The new coordinate system's origin has a coordinate in the old coordinate system. It has to be given to us. Let's call it center 1, center 2, okay, or cx, cy. Let's call them cx, cy. The new coordinate center of the coordinate is given to us in the old coordinate system, cx, cy, and our goal will be to figure out these vectors should also be provided to me. For example, the new x coordinate is the vector 1, 1. The new y coordinate is the vector minus 1, 1. Okay, look at this. If this is the new coordinate system, what is the new address? What is the new coordinate of the point in this new coordinate system is another thing we will try to find. And the answer will be multiplying the old p with a matrix, okay, to find this p new. We will in 2 dimensions, we will be multiplying it with a 3 by 3 matrix and to find the new coordinate. Okay. Oh, okay. Thank you for the comment, Bugra. Yeah, the whiteboard. I really feel like I'm teaching in class when I'm using the whiteboard, because in class I'm also using the board a lot. And I think it's the progression is more natural in the whiteboard. I also agree with you. Yes, slides are too quick to follow. Everything is given at once. I mean, even if you're going step by step, you're just reading them. The derivations of like these modeling transformations, I think it's much more effective when using the whiteboard. Thank you for the comment. And yeah, that's also really interesting, right? Look at the new problem, the camera transformation. Somebody gives you, changes the whole addressing. This is my new coordinates origin. These are my new axes. What is your new address? How can you find that? You're going to see that. We will be just using some rotation and translation to do that, and it will just be another 3 by 3 matrix. All right, so thank you for attending. That's it for this Monday. See you all on Thursday, and we are going to continue with this topic. All right, take care. See you on Thursday. Bye-bye.